Hello, everyone. Thanks for calling in and linking in on today's presentation. It's Troy Hagel here talking from Whitehorse, and I'm just going to kind of give a little bit of an intro here, and then pass everything over to Leonardo and his colleagues with Apex Resource Management. But basically, bit of a history. This is they're going to be providing kind of a technical overview of this DGSim, this population simulation model that's kind of been in the works for a number of years now, and we've most recently been Leonardo and Colin and Josie have been working with us on a little bit of modeling work with the on the Fortymile herd, and looking at some harvest scenarios and that kind of thing. But because of that recent work, we thought it would be a good opportunity to actually have this presentation to give a lot of people an idea of what this model is about. I know I've tried to explain it and give an overview of it in a number of different places, but I think, you know, having Leonardo and folks do this is they'll probably do a much better job than I ever would. So yeah, we decided that because there's so many people on the line, we're not going to do introductions or anything like that, because that will just take too long. A couple housekeeping things. So Leonardo is recording the presentation, so just be careful what you say. And also, if you're on a speakerphone, maybe just mute it, because there's so many people that if there's a whole bunch of background noise, it could get really disruptive during the presentation. And then also, there's on the little control panel, there's a chat box. So if you do have questions during the presentation, Leonardo suggested just write in your question in that chat box, and at the end of their presentation, there'll be a lot of time for questions and answers. And so whether the questions are on the chat box here, or just you know, through the phone line, they can address those questions. So we've got 2 hours scheduled. I don't think we're going to need 2 hours, but I'm pretty happy that there seems to be a lot of interest. And I think we're covering, like, I don't know if Jason's on the line, but if he is, like, we're covering like a huge number of time zones and multiple jurisdictions. And so I think that kind of speaks, there's a lot of interest in this, so that's pretty cool. But without any further ado, I'm going to pass things on to Leonardo and Colin and Josie, and they can take it away.
Great. Thank you very much, Troy, and thanks to everybody who's on the line for attending the presentation. What I'm going to be doing is starting out with a few slides that give an overview of what DGSim is, and then I'm going to jump into an actual live demo of the software, kind of showing the software using the recent work that Troy mentioned that we did with the Fortymile Caribou Herd. So DGSim is a general age structure population modeling framework, and it's been funded by various government agencies, so it's available for free as a result. And some of the key people who have been involved in the development of DGSim include Craig Nicholson, who originally developed kind of a spreadsheet version of this of the calculator that then DGSim morphed into DGSim. Also, Don Russell with the Circum-Arctic Rangifer Monitoring and Assessment Network, or CARMA. Troy Hagel, of course, and more recently, Christine Kyler with the Government of Greenland. And the DGSim, the model, has been around for about 4.5 years. And since then, it's been applied to a number of herds in Canada and Alaska, and also more recently, it's also been applied to 2 muskox and 1 reindeer herd in Greenland. Now, It is an add-on to a software framework that we developed that's a generalized time-space stochastic simulation modeling framework called SynchroSim, and it includes other add-ons. So one of the most popular ones that we developed is STSim, which is used for modeling landscape change. But the key thing about the framework is that because it's had a lot of support for development from other agencies, like the ones shown here on the bottom right, is that it's made it possible for us then to develop this population modeling framework on top of that for relatively low cost. So the way that DGSim works is you start out at a specific point in time and you want to make projections about a population. So here we have an example where we might have a total population size of 56,000 animals. And we break up that population based on an inventory according to age and sex classes. And these age and sex classes are going to be typically defined by A, what can be observed when you're conducting your inventory, but also ecologically by differences in demographic rates according to the age classes as well. So we then want to be able to take this age structure population and make projections about what that population might look like in the future. And so to do that, we need a number of parameter estimates, and those include the annual rate of harvest, so how many individuals, and this can be specified either as a rate or as an absolute number. In this case, we're showing them as an absolute number. The number of individuals in each age and sex cohort that are being harvested each year. We also need estimates of mortality rates, again, and these can be specified by age and sex cohort. And we need estimates for the females specified by age of their fecundity, so how many offspring per year each female will be having. And so that defines then for the following year how many new individuals are added to the population. And finally, at the end of kind of the simulation year cycle, we need to age each individual cohort and move it on to the next age and sex cohort. And given all of those parameter inputs, then we can make a single year projection of how many individuals there will be in each age sex cohort the following year. And if we repeat that for a number of years, then we can make a projection over a number of years. Now this represents kind of a single Monte Carlo simulation of the model. As you all know, when we make estimates of both population sizes and demographic parameters, there's uncertainty associated with those estimates. And so we incorporate that uncertainty by not just running a single model projection using a single set of values, but for each of the demographic parameters, we usually have an estimated probability distribution of the values of those parameters. And so for each Monte Carlo simulation, we sample from that distribution. And I'll be talking a little bit about more about that, how we did that with the Fortymile Caribou Herd when I jump into the demonstration. So one of the things that you can configure in the model is the annual cycle or the order of events as they happen. So what I'm going to show you now is the order of events as we configured them for the Fortymile Caribou Herd, but these could be different if you're configuring them for a different herd. And so the simulations that I'm going to show you with the Fortymile herd are assumed to start at the beginning of October, and this overlaps with the composition surveys that give us estimates of the proportion of individuals in each age and sex cohort in the population. And then we project forward, first applying the harvest. So we remove individuals from the population. We also apply for calves the mortality that's associated with the October to May time period, which tends to be a lower rate than what happens between the May and October time period. And we apply adult mortality throughout the year at a constant rate. On May 18th, we age all of the existing individuals in the population by 1 year, or all of the cohorts. And then we add new calves to the population based on parturition rate estimates. Now, there's also a photocensus conducted sort of in the summertime between mid-June and early July, but that's not included in the model. And the reason that's not included is currently the software only allows for one census time period. But I'm just putting that here because I know people will be aware of that photocensus. And then between the time of parturition and the October 4th census, we apply mortality to calves. And for that time period, the mortality rates are quite high for calves. So then back on October 4th, we then output the number of individuals that are in each age and sex cohort. And that's whenever I show outputs for the model, those are based on October 4th dates. Now, a little bit of info for those who are not familiar with the Fortymile Caribou Herd, and this is from a recent paper by Borchi and others. Most of the range of the Fortymile Caribou Herd shown by this red line here is within Alaska, but particularly as the population has recently increased, there's individuals that are starting to be observed in the Yukon as well. And speaking of historic changes in the population, so again, from that same paper, we have estimates, and I believe these are mostly minimum count estimates back from the late 80s to the present, showing a steady increase in the size of the population. And also of note, there's a time period between 1994 and 2003 when there's quite a lot of detailed data on calf survival, which was made available to us, and so it was very helpful for us to estimate those demographic parameters. So based on the starting point of when that high detailed data on calf survival was available, we and I'll be showing, we conducted retrospective simulations from 1994 to 2017, which is the most recent minimum count. And then we also conducted prospective simulations from 2017 to the year 2022, so for a 5-year time period. So I'm going to jump over to the software now. Okay, so this is the DGSim software, and the first thing that you see on the left here is a list of what we call model libraries. So these are actual files on disk that contain different kinds of models, and just as an example, I'm showing that you can have different models for different caribou herds, and in the case of this one here, we have also a model for a muskoxen population using DGSim. Now, what's defined typically at the level of the project, what we call a project, are some of the basic classifications that you're going to be using in the model. So, for example, for this muskoxen population, we've decided to use age classes, 4 different age classes that include a 5-year-old age class. And the reason that was decided for that population is because the 5-year-old bulls are of particular interest to the people in this area, the number of 5-year-old bulls. Now, for the Fortymile Caribou Herd, we defined 4 age classes as well, but a slightly different configuration. So we've separated calves, subadult, adults 1 to 2-year-olds, 3-year-olds, and then 4 years and older. And I'm going to go through all of the model inputs that we use for one particular scenario, which is a retrospective simulation from 1994 to 2017. So on this tab, we define the starting year and ending year. And we also, for the demonstration purposes right now, we ran the model for 100 Monte Carlo simulations. Now, when we do full production runs, we usually run the model for 1,000 Monte Carlo simulations, but that makes the software a little bit slower to demonstrate. So that's why I've chosen 100 for this particular demonstration. And we're starting out on Julian Day 276, which is the reporting date. And as I said, that's the equivalent of October 4th. Now, we need to initialize in 1994 the number of individuals in the population. So in 1994, the minimum count is somewhere around 25. Actually, the minimum count is somewhere around 22,000 individuals, but we included some uncertainty associated with that minimum count. And then we also need to define the starting sort of age-sex structure of the population. And so that's shown here. That really defines the number or the relative proportion of individuals in each age and sex class. You'll see that for the females, we have more resolution in terms of the number of individuals by age and sex class, whereas for the males, we only have specified the number of calves and the number of individuals 1 year or older. And that data comes from data provided to us by Troy and Mike from ADFG. So you can see, again, similarly, there's more resolution in terms of the age structure of the cows than the age structure of the bulls in 1994. The other set of inputs that we need to specify include the demographic rates. So here we specify the number of offspring per female. We specify that the birthday is on Julian Day 138 or May 15th. And then we also specify that the number of offspring per female varies according to whether the females are 3-year-olds or 4 years and older, and that there's also variability in time. Now, you can't see this here on the screen, but we also specify variability between Monte Carlo simulations. So I'm just to show that, I'm going to export this out to Excel. And so we can see here that if I click on the filter toggle, we have values specified for all 100 Monte Carlo iterations in the model. And I'll explain a little bit more why we need to do that in just a second when I show you where this data comes from. Oops. So here are observed parturition rates for 3-year-old females, and the actual raw data behind this particular figure was provided to us. And so we were able to, using Bayesian mixed logistic regression, this is work that Josie, who's on the line, conducted, come up with estimates of uncertainty around both years in which the parturition rates were actually observed, but also because of the trend in the data, we were also to make estimates of potential future rates of parturition for 3-year-olds. And so when we run the model, we're not using just the dots, but we're sampling from a distribution that's represented by these 95% credible confidence intervals. And the same is true for 4-year-olds. So for 4-year-olds, you can see that the observed parturition rates tend to be higher, and there also tends to be a little bit less uncertainty around those rates. The other thing is that when Josie did this analysis, she found that there was a correlation between the 4-year-old and 3-year-old parturition rates. And in the model simulations, when we sample from these distributions, we're able to maintain the correlations. And so that's why for each time step in the model and each Monte Carlo simulation, we specify a different value sampled from these distributions. Oops. So those are the number of offspring for female. We also specify mortality rates. And just as those rates can vary according to age and according to sex. And for calves, as I noted earlier, mortality rates vary according to time period. So between Julian Day 138, when they're born, and Julian Day 276, mortality rates tend to be quite high. And then after Julian Day 276, mortality rates for calves are lower. So again, just to show you what that data actually looks like. So here's the May to October observed mortality rates for calves. And here are the 95% Bayesian credible intervals. And you can see that for starting in 2003, when we no longer have data, there's a lot more uncertainty in the distribution that we're including as an input for calf mortality rates. And so you'll see that in the model projections, starting in that year, there starts to be more uncertainty around the model projection of the number of individuals in the population. And here is the observed mortality rates from October to May. And so you can see they tend to be lower, but there's, moving forward, the mean of that distribution is low, but there tends to be a bit of a long tail to that distribution in terms of the uncertainty around future mortality rates for calves. And this is just the observed mortality rates for adult cows. Now, we didn't have the raw data, so the credible intervals had to be derived from the parameter estimates out of the Borchi and others paper. So those are mortality rates. And finally, the last piece of information that we need to specify is the number of individuals harvested. So we had, and again, this can vary by year. In this case, we had, for the retrospective individual, information on how many individuals are harvested. So we didn't have to include uncertainty around that. And here's just a figure that shows the data that we use to specify the number of individuals harvested. And you can see most of the harvest over this time period is happening in Alaska, and most of it is bulls. And there's a little bit of harvest of bulls in the Yukon towards the end of the time period. So those are all of the inputs. And what does that mean for the model projection? So what I'm going to show in terms of output are the projections for that retrospective simulation. And I'm also going to show for the years when it's available, the photocensus minimum counts from 1994 to 2017. So again, here we have time on the x-axis from 1994 to 2017. The blue line and the shaded area represent the 95% Monte Carlo confidence intervals for the projection. And then the red dots, and when there's two contiguous years in a row, you'll see a line between them, represent the minimum count estimates of the population. We can also look at other forms of outputs for these projections. So here, for example, we have the age structure of the population in 2017. So we have, we can see that both there's quite a bit of overlap between the 95% confidence intervals for the projection versus the count data. And I believe we didn't have the age structure we didn't have for 2017, so this is actually the age structure. We use the same age structure for 2016. So it'd be probably a little better to compare against 2016, the age structure. So those are the retrospective simulations. Now, aside from doing past or retrospective simulations, we ran a number of future scenarios exploring a variety of different, doing sensitivity to a variety of different factors. So we ran kind of a status quo simulation, but then we did things like vary the amount of harvest that's happening in the Yukon, varying parturition rates for 3-year-olds, varying cow survival rates. I'm not going to go through all of those scenarios, but I've kind of selected 3 of those to look at here. And so those include kind of a status quo scenario, which takes into account that there's been roughly about 2.6% harvest rate on the population, with a little bit over 2% harvested as males and about 0.5% harvested as females. Another scenario which is similar to that, but in which the Yukon uses its full quota of 35% of the harvest. So that would bring the harvest up to about 4%. And then finally, we ran a scenario which is the same as the status quo, but we reduced the survival of adult cows by 10%. I'm just going to close this chart now, and I'm just going to run these. So I can right-click and select Run. And this usually just takes, the model's quite fast with 100 Monte Carlo iterations, so it usually just takes about 20 or 30 seconds. Here the runs are complete. And so now we can look at future projections, and I'm just going to start in 2017, and I'm also going to remove the past projections from the results so it's a little bit easier for us to see. Okay, there we go. Okay, so now we're showing in blue kind of the status quo scenario. In red, we're showing a slightly increased harvest scenario. And in green, we're showing the scenario in which there's a reduction in cow survival rates. And we show both the projected mean across all of the model iterations, and then also the shaded areas, the 95% Monte Carlo confidence intervals. And we could look, this is just the total population, but we can also look at the total population, this time without the shaded confidence intervals. At the top, we show the population, and then we show the number of individuals being harvested. So you could see that the red scenario, where the Yukon uses its full quota, is increasing the number of individuals being harvested by about, well, it looks like just under 1,000 individuals. And this is assuming a target harvest rate of 4%. And then we see that both of the first two scenarios show an increase in the population, but a decrease in cow survival by 10% would project both a decrease in the total population size, and because harvest is based as a percent of the population, also a decrease in the total number of individuals being harvested over time. So the next thing I want to show you is we have two interfaces for this model. And what I've been showing you so far is what we call the full interface. But we wanted to also create a bit of a simpler interface that allowed only certain, where a model that had already been created could be used by stakeholders to conduct sensitivity analysis, but not be exposed to the full complexity of the model. And so that we call DGSim Lite. And what I'm going to do is I'm going to take these these three scenarios that I call public scenarios, and I'm going to publish them to the Lite folder. And so then now I can open up the Lite version of the software. Whoops. Oops, I forgot to do one thing. I just have to save the library after I publish the scenarios. So I open the Lite version of the software, and then I'm going to open up that particular library. And so we see those same three scenarios that I put in the public scenario, and we've already got results for those three. And I can, if I highlight them, I have access to be able to view the same charts that have been configured in the full version of the model. The other thing I can do, however, is I can also say, take a scenario and say, well, I want to be able to vary the harvest rate and see what that does to our future projections of the population. So I'm going to take this scenario where we have 4% harvest rate, and I'm going to make a copy of it. And then I can click on it and open, and you see we don't have all of the same inputs which I showed you earlier. It's a limited number of inputs in this version. And I'm going to rename the scenario where we apply a 6% harvest rate to the population. With 4% as males being harvested and 2% as females. And under annual, so we have the run control. I'm not going to make changes to the projection time period of the number of Monte Carlos. And actually, rather than specifying these values, we're going to start the simulation in 2017. So I don't need to include all of these time steps here. And starting in 2017, I want to harvest, we said 2% of the population as females and 4% as males. And again, because we're not running the model prior to 2017, I don't need to include all of those prior time steps as well. So I can now save my changes. And I'm going to just select that scenario and select to run. Okay, and the simulation's complete. I'm now going to compare it against the base scenario where we are harvesting 4% of the population, and we can show population and harvest. And so you can see that the scenario where we're harvesting 6% of the population is showing a slight decrease. We can include the 95% Monte Carlo confidence intervals in that. And we can also see starting out harvesting a higher number of individuals over time. The other thing about this light version of the model, which I thought I would mention, is that because this was partly, the funding for this was partly developed using funding from the Greenland government. They wanted to be able to bring the model to stakeholders, so hunting communities in Greenland. And so we actually included an option to be able to show this light version in Greenlandic. And so I need to restart the software to be able to show that. And so now we have it in Greenlandic, and I'm going to open up a model that was configured for that population. Oops. Here we go. So here's a scenario which was configured with inputs in Greenlandic, and it was built together with stakeholders in a small hunting community in Greenland for this particular muskox herd. And then a third interface that we have for the software, so often when we're working with large data sets, it becomes a lot easier to use a scripting environment. So we actually, and the work done for the Fortymile Caribou Herd by Josie to build and parameterize the model was using this R package that we've developed for the software. So we've got a library called RiskMan that's documented, and this library allows you to get access to all of the model inputs and outputs and be able to essentially create a model from scratch, parameterizing right in the R environment, and also be able to produce plots of outputs. So again, for example, here's a plot for some of the simulations that we're doing to explore different rates of harvest. Different panels represent different fills in this chart, different fill rates for the Yukon in terms of the use of their 35% quota, and then the different rows represent different harvest rates, so 8%, 6%, 4%, and 10% harvest rates on the population. So that's just an example of it can be very powerful to be able to build the model and interact with it through the R environment as opposed to directly in the user interface. And I'll just end by pointing you to our website. If you have questions about DGSim or want to be able to download it, you can go to the home page and go to the Caribou Simulation Modeling page, and there's a link to be able to download DGSim here, and we've got a few videos as well showing how the software is being used elsewhere. I'll be happy to take questions now.
Leo, I see a couple of questions in the chat box.
Okay.
If you want.
I'll go. I'll go scroll through that. Here we go. Okay, why does the model use a census on October 4th when the photo census is always conducted in late June, early July? Yeah, so there's two inputs that we parameterize when we initialize the population. One of them is the total number of individuals, but we also the composition of the herd in terms of the number of individuals in each age and sex cohort. And the composition surveys are conducted on October 4th. And the composition of the herd can be quite important in terms of the growth rate of the population. And because we are limited with only doing one census, we opted for running based on the composition surveys rather than based on the total population size. We could, of course, reconfigure the model and assume the composition doesn't change much between June, July, and October, and run the model that way. So that could be an option, but that's the reason we chose to run from October 4th. Does that answer your question?
Yeah, that makes sense. And then,
okay.
Holy cow, that
yeah,
I got
a bit of
some
an
knee jerks there.
echo.
Yeah, that makes sense.
Then
I had a follow-up question there.
Okay, yeah. We could consider doing a composition survey during the same time frame we normally conduct mono census. Would this improve our ability of the model population versus a photo census? You know, I think there would be some, if there was, yes, it would improve slightly, because we're kind of assuming when we first initialize the model, we're using the number of individuals in July to initialize the model in October. So I think it would be a slight improvement to be able to have those two match up with each other.
And I wouldn't foresee switching our comp strictly to July, but it would be an additional survey. They do that with Nelchina. We've knocked it around in the past, and we didn't do it just because we weren't doing models like this, and it wasn't serving too much purpose.
Yeah,
so,
I mean, I don't know what if it would be a very high cost. I mean, if it's something that would be relatively easy to do, then I think it would make sense.
Well, one thing you might want to do, it's Colin here, is do a bit of a sensitivity analysis in the model to just see how sensitive your projections are to, different assumptions about errors you're getting, and because of this, and see if it really makes a difference before you go out and do the change.
Yeah, I think that makes sense.
Also, sorry, this is Josie here. One could consider reconfiguring the model to acknowledge 2 census points.
Right, and then use that reconfigured model to even better estimate the sensitivity of your projections to the different census points.
Yeah, rather than changing the data, one could sort of adjust the model to match the data better in terms of timing.
Okay, next question. Yeah, so you had a question about bull to cow ratios for that scenario. We could take a look. Just a second, I'm going to move this out of the way. And I'm just going to refresh this. So here's the, just going to bring up the scenario that we just ran. I'm not sure why I'm not seeing it here. Here we go. So here's a scenario that we just ran in the light version. And I'm going to add it to the results. And you were wondering about the bull to cow ratio. So here we go. So here's the bull to cow ratio, but I'm going to show it over time. So 2017, and, line chart, 2017 to 2022. So you can see that we're starting, unfortunately, we're not showing sort of proportions, but you can get a sense of the total number of individuals. And so this was, we're seeing that with 4% harvested as bulls and 2% harvested as cows, there is a slight change to the population sex ratio, but it doesn't look that high to me.
You could export this to Excel and do it pretty quickly.
Yeah, sure,
Leo,
why
get
not?
the actual
That's a good
ratio.
idea. So we'll just export all.
Export all.
Yeah.
And currently, I think we have an objective of, I think it's 35 bulls per 100.
Okay, so let's
That's
just see.
something that we're going to want to talk about
So bulls
as we develop new harvest strategy.
So this is going to be equal to the mean number of bulls divided by the mean number of cows times 100. Okay, so we got 45. We're starting out at 45 bulls to, wait, is that right? Hang on. Yeah, bull to cow, yeah, this is the, so 45 bulls for 100 cows we're starting out, and we're not seeing much of a change. Yeah, it's staying relatively,
Wow.
slight decrease in the number of bulls to cows for that harvest rate.
Yeah, at least nothing that occurs quick enough that we couldn't monitor it.
Yeah, we did run some scenarios where we looked at bull only harvest, and I do have a figure from that because we just ran those yesterday. So here is, just to kind of give you an example. So this is scenarios in which only bulls are being harvested, and it's well, the status quo includes some cows, what I showed you in that figure, but then 2% of the population harvested only as bulls through to 10% of the population harvested only as bulls. And you can see that once you start to get above 6% harvest rate, where you're harvesting only bulls, there starts to be a very rapid decline in the number of bulls to cows.
Yeah, and I was figuring we might be better off to get closer to a 50-50 bull, male bull harvest, at least like a 40% female is kind of what I
had
in mind.
Yeah.
Anyway, yeah, it looks like you got a lot of scenarios there though.
Okay, I'm just going to look to see if there's other questions here. Okay, so that was the last question on the chat window. I don't know if there's other questions just on the phone.
Hey, Leonardo, it's Troy here. One of the things I think that's really useful in kind of the new work you guys have done is the R package, because it gives a lot more flexibility to deal with, I'd say, raw data, and then importing it into the model, and especially, especially with the kind of the covariation patterns like you described for 3-year-old and then 4-year-old and older parturition rates, just for example. But I'm wondering if you could you or Josie or someone just give just a little bit of a better description of, how do you pull that, or how do you link basically kind of statistical models in R, and then take do your sampling essentially in R and port it into DGSim. And then I guess and a kind of a follow-up question is if you could show then how you specify your distributions for your vital rates in the absence of, say, by iteration, just by specifying your mean and your min-max standard deviations, that kind of thing. Because I think both of those are really useful. To some extent, it depends on what kind of data you have.
Yeah, so I guess there's a few questions there. So the R, and Josie, feel free to jump in at any point, but basically the R package gives you access to all of those tables that I showed you in the interface using what we call data frames in R. Let me see if I have any examples of actual ones here. Well, let's just see. I'll just run some code here. So hang on a second. Actually, it's going to take a little bit too long for me to do it ad lib, but essentially you can pull in, all of those tables can be pulled in. So for example, here's a list of all the scenarios. And similarly, just as I showed tables in the user interface, you can pull them in as data sheets. And so if you're running your analysis where you're making estimates for your population parameters, and you can sample for those distributions in R, then you can fill in those tables directly using this environment. And that's essentially what Josie did when she created those tables of parameter inputs. So for example, number of offspring per female, again, are sampled from a distribution in R and then put directly into the library. Now, Troy mentioned another approach that you could use, which is to say, rather than sampling from a distribution in R, the software has some built-in distributions that you can use. So if I create a brand new scenario that has nothing in it right now, and I go to the demographic parameters and the number of offspring per female, I can specify a minimum, a maximum, and a standard deviation. And again, I can vary that by age class, but let's just say that you knew that the average number of offspring per female was 0.6 or some other value, and then you could define, and the model currently is being built because it was based off that Caribou calculator that used beta distributions, which are quite flexible in their shape. Right now, DGSim is kind of limited to using beta distributions when you're using the built-in sampling. However, it would be not a lot of work for us to be able to extend the capability. Some of the other model plugins that I discussed earlier use other types of distributions like normal and uniform, and you can even create your own custom-built distributions. So it wouldn't be a lot of work to extend the software to be able to add your own custom-built distributions to it.
I can jump in here and say a few more words about how we did this particular Bayesian estimation exercise and how that fits in with the SynchroSim. So in this particular example, I used the package rstan-arm, which is a fairly recent package based on the STAN software for Bayesian estimation that essentially makes Bayesian estimation of generalized linear mixed models not much more difficult than frequentist estimation of the same models. So people who are accustomed to fitting mixed models will find the interface familiar. And that package sort of comes set up to sample from the posterior probability distributions that are estimated from the data in a way that essentially the package produces tables that can just be loaded directly as parameter estimates into SynchroSim. So they fit well together, and for anyone who has experience in the past using Bayesian estimation, I will say that the process is much easier and automatic and less painful than it used to be. Is there any other questions about that or comments?
Well, it's Colin here. I'll just make one more comment about the R package way of interacting with DGSim. One of the big benefits of sort of parameterizing your model, basically going wall to wall, as I call it. So starting with your data, writing all the script to estimate the parameters, creating the scenarios, processing the output and plotting it all in one long R script or in two or three of them, is the reproducibility that gives you of your workflow. So you do all this work, you parameterize all these models, and then you find something you want to change or something's wrong, or a reviewer says whatever about asks you to redo something or change it. You've got everything there in a script, and you can reproduce it very quickly in the future, and also pass it on to other people sort of for peer review. So that's what we found since the R packages come. We just try and do all our work now in that script environment for that very reason, that it becomes reproducible in that way. Of course, that requires that you know how to work in R. So it's not for everybody, but for those that are comfortable with it, it's very powerful.
Did that answer your question, Troy?
Yeah, no, that was great. It was more just just to kind of describe it a little bit more. But no, that's great. And actually, I had one other point, Leonardo, and I don't know if this isn't a question either, but back on the graphs that you showed, where you had the 95% credible intervals for the kind of the future estimates of whatever vital rates, like it was on the PowerPoint itself. Maybe just to explain, like those bars essentially represent a distribution, with the red dash being the mean, so that, you know, if you're sampling from within that bar, that range, the most likely values are going to be near that mean. And so some of those at the tails there, you know, down at the lower end, it's going to be much rarer. Am I correct on that?
Yeah, it's not. It's definitely not a uniform. No, it's definitely not a uniform distribution. I mean, we could. I don't have a plot handy, but if you wanted to see, you know, the probability density function for those, I think, Josie, correct me if I'm wrong, but I think we could provide them.
Yeah, absolutely. And yeah, it's not a uniform, and it's not even a Gaussian. It's bounded between 0 and 1 there, so it's
yeah, I mean, just from an interpretation standpoint, because, you know, you can look at that and go, whoa, that's really a wide range, but it's not really maybe as wide of a range as it appears. Just if you were to imagine like kind of a asymmetrical bell curve or something on there.
Yeah, exactly. And I mean, so the fact is that range is wide because we have quite a bit of variation in the past among years. So you can sort of see that there are years in the past that fall more on the tail of that distribution, but not that many of them, yeah? So the one in maybe 2003. So essentially the distribution there is meant to represent, or it's informed by the distribution in the data points we have.
Ms. Marcia, if we had a better idea of why that annual variation happens based on climatic or other variables, could we reduce that variability annually if you know
what the climate's going to be like in the future? Or?
Well, yeah, I guess we're future projecting, yeah.
Yeah, I mean, if you had some relationship and you had climate projections, then you could include that.
When you're doing if you don't have those variables, you're not doing like even when you're back projecting in the time periods when you don't have the detailed demographics, you might be able to set those rates.
Yeah, yeah, that's true. That's right. So like here, for example, the CAF data, we only have until 2002. And you're right, that has a big impact. Like if we go back to the model projections for the retrospective simulation, we look at the projection. I'm just going to show only till 1994 to 2017. You can see that as the uncertainty in the retrospective projections gets much higher after 2003, where we no longer have the CAF survival data. So I think if you had climate data to be able to inform, then the confidence bands around the retrospective projections would become much narrower.
And this whole model reminds me of RiskMan quite a bit. Are you familiar with that tool?
I'm not. Colin, are you familiar with it?
Yes, I am. Yeah, it dates me a bit, but I was involved in the initial meeting of RiskMan a long time ago, so I know a bit about it. There are some similarities. You're right, because it's stochastic and it was intended as a general demographic model. So in terms of approach, there are some similarities. It was built first and foremost to deal with polar bears, and so it deals. The DGSim here has at the moment. I mean, we could expand it to do more of what RiskMan does, but It doesn't deal with multi-generational, mothers and cubs, across years, right? It's got very simple population dynamics, whereas RiskMan had much more complex stuff because it had to deal with polar bear population dynamics in particular, so they built it around that. So it's got more complexity, I would say, as a model than what we have so far. The other contrast is, as Leo mentioned, what we've done here sits in the SynchroSim piece of software, which is had a huge amount of funding behind it, which is what allows you to do all this interactive graphing and exporting and importing Excel, and gives you an R package link, and all those features of just data management come for free to DGSim because we have them through in a framework. Whereas RiskMan was developed quite a long time ago now as a one-off, and so I know people still run it, but it's extremely dated and limited environment in which to run compared to this. So those would be the main contrast. But in terms of overall approach, yes, scientifically they're quite similar.
Thanks.
Sorry about that. We do have ongoing parturition rates and fall calf cow ratios from comps, and then we have been putting calf or collars on 5-month-old or 4.5-month-old female calves post 2003, and that could give a potential idea of calf mortality.
Yeah, right. And I know, last week I got a little bit more data from Mike Suter. I think there's some 2016, 2017 calf survival that we didn't have time to build in right before the presentation, but that's something that we can build in as we finalize the scenarios that we're going to be running over the next week or so.
This is Torsten in Fairbanks, and related to that new calf survival data, you had a figure in your PowerPoint presentation that looks a lot like the one you've got on the screen now, but with the photocensus points in there. Can we look at that one again?
Sure. So the one from the paper, the Borchi paper?
No, it looks just like the one you've got on the screen here, but it has the photocensus population estimates
on the presentation.
Also.
Oh, I don't think I had a population projection with photocensus on the. Oh, it wasn't on the PowerPoint, but I know what you mean. This.
Oh.
So these, and I'm just gonna hang on one second. I'm just gonna remove this one.
Okay. Yeah. Right.
This, right? Yeah.
That's perfect. So I just want to make sure that I understand how the confidence intervals work and your population estimates, your modeled estimates. So you start in 1994 and you have a population estimate, and then is your modeled estimates just using the survival and composition data? It must reset each year using the photocensus data, it seems to me.
Yeah, no, so this particular projection is only being set in 1994, and then all subsequent time steps are only based on the demographic rates that are provided. We're not resetting the start of the model back to the photocensus minimum count with this projection. But the one thing that we did do with this projection is we don't have bull survival data.
Right.
So we calibrated the bull survival data for this projection to be able to match the photocensus counts, particularly for that early time period where we had photocensus counts for every year. So that was the calibration is making changes to the bull survival data, and we wanted to calibrate both to the sort of age, sex structure and to the population size.
So the reason the confidence interval stays tight through 2003 is just because of the calf survival data, not because there's more photosynthesis during that period.
That's right. It's because of the calf survival data. Yeah.
And then I know when Mike talked to you about the new calf survival data, I mean, we only have a year and a half of data so far, but it's similar to what Rod had. We can't, if it's different, we don't have enough data yet to say how it is different.
Yeah, that's right. I think he showed it to me, and it's kind of within the range of the I think the calf survival data seemed to be within this, it was somewhere around the middle of this range here. And so it seemed reasonable to just continue, at least for this for the presentation, to just use the estimated distributions that we had already.
Yeah, I'd agree with that. So, but how would adding the new calf survival data, would that shrink I guess you'd start with a new population estimate, and you start with those tight confidence intervals, like you had back in your 1994 simulation.
Well, I think maybe Josie, you might be better able to answer that question, because these guys have some calf survival data for 2016, 2017. Is that right?
That's right.
So we would keep kind of the data points that we have from earlier, I would assume, but bringing in those additional data points would hopefully reduce the uncertainty for projecting from 2017. Is Josie?
Okay. Yeah. So if we add another couple of data points to what we're seeing here on the screen, it would reduce the uncertainty for years where we don't have data a little bit, but maybe not a lot, in that you can see a big part of that uncertainty about the year that we don't have data is simply because there's quite a bit of variation among years in the past. So I'm not sure that it would certainly reduce our uncertainty about predictions for which we have data, but I'm not sure it would reduce the uncertainty a lot for years when we don't have data. Does that help?
Yeah, thanks for going through that.
Any other questions?
Yeah, Leo, it's Don. Just a quick one. All your projections involve a rate of harvest percentage rather than historic harvest.
Yeah.
In reality, harvest rarely responds to changes in population size. It tends to be more of a ratchet effect. Once it's up, it stays there until management decisions are made. That'd be easier to apply, I would think, if you kept it at a high rate as the population is going down.
Right. So I think what Don's saying is, if instead of specifying harvest 4% of the population, you would specify harvest X number of individuals. And that's the way we ran the retrospective simulations. So here we set the harvest as an absolute number of individuals. Sorry, the reason that you're seeing decimal points here is because we had total harvest and we had a ratio of males to females in the harvest. But really these are going to be number of individuals harvested specified here. You could run future scenarios specifying number of individuals harvested rather than specifying percentage of the population if you wanted to.
But I'm wondering, Don, are you suggesting that if you're modeling in the future, you might have some sort of rules about, like, we're going to hold this harvest for forever at this level unless the population drops below this threshold, at which point we'll cut it down to this and hold it there until it rises back above this threshold? Some kind of rule like that would better mimic into the future what you think harvest policies are?
Well, you can apply harvest policy at any given time, change the sex ratio of the harvest, or recalibrate it to, if you want to keep it at, say, 4% harvest, it's there until you reevaluate the current population size and then make a management decision that because it's crept up to now 6% of the harvest with a declining population, you're going to reduce that overall take.
Right. So so correct me if I'm wrong, Leonardo and Josie, but I don't think right now we can have harvest policies like that where the harvest is somehow a function of, say, the population size.
You can't easily do that. You could using breakpoints. And so if you ran your model from R, you could run it 1 year at a time and have it take a pause and sort of, but it would be very complicated, not easy to do straight out of the user interface.
So yeah, I guess that the answer there would be sort of modeling some of those policies like you're suggesting, Don, is possible, but it'd be a more advanced thing that you can do currently with the model. You can pause and reevaluate and implement your policy dynamically, but you have to do that with our R version. There's no lever on the user interface to kind of set that kind of thing up right now, unless we added it, you know. But
okay, thanks.
All right, Marsha, I'm just trying to understand the clarity on that. So basically, right now you're adding it as a percentage of the current population, not as a, like the harvest is set at 200 animals.
Yeah, for all of the prospective scenarios which I showed, we set the harvest as a percentage of the population on that time step. So that's why, for example, the scenario which showed a decrease in the population also showed a decrease in the harvest. But there is the option to instead specify it as a fixed number of individuals.
Yeah, thanks.
So you can do one or the other, but you can't have this easily on the interface, this idea where you make the harvest, whatever it is, whether it's a percentage or a number of animals, a function of some other variable that's changing in the model, unless you do it through R.
Okay, so this is Jeff Gross. To clarify a little further, the model then, you have fixed percentages, so the model is adjusting the actual number of animals harvested based on the projection of the population trend using the fixed percentage. Is that correct? So actually the number of animals would change, it would not be fixed over time?
That's correct. So I misstated it, right? So you can set a fixed percentage or a fixed number of animals, either one of those. So if you pick the percentage, then the number actually harvested will vary as a function of your population size. But what you can't do is change the percentage as a function of population size, right? Easily, you can, but that's quite a bit more complex. So to say, when I hit 50,000 animals, I will then allow the harvest rate to go from 4 to 6%. That's harder to do. It's doable, but we didn't do that kind of thing.
Yeah, I mean, leaving it using projected population estimates. Yeah, you get out a few years, that's starting to really split hairs with caribou management, especially when we're getting population estimates potentially only every 4, 5, 6 years. But anyway, yeah, it's interesting.
Yeah, so based on what you're saying, it might make more sense to say fix the harvest at a set number of individuals. I think this is what Don was saying too. The population today is 100. We want to harvest 10 individuals a year. We might not know what the population is going to be for the next 3 years, so we're going to keep harvesting 10 individuals a year for the next 3 years.
But Don,
right, and honestly, the trend. Looking at the trend, if we can get a reasonable harvest rate, doesn't seem like the actual number would change all that much over time anyway, and it's generally easier from a management perspective to be able to tell the public, a specific rate, because honestly, we get at the end of the day or the end of the year, we're never right on anyway. We're always a little low, a little high, and again, it's just kind of a little bit of splitting hairs with the population or the harvest level we're talking about here from this herd.
I'm I just quickly looked on the Porcupine PCMB harvest webpage, and they have that there's zones for hunting, right? And so I'm wondering, to model something like that we'd have to be more sophisticated if you wanted to model that sort of approach and see what its effect was on the population under different uncertainties into the future. I think we could do it, but that would be an example of something more complicated.
You said the porcupine herd has zones?
Yeah, the porcupine, like it says, I'm just looking, and maybe Troy or Don or somebody else who knows the herd better can sort of explain it. Can you explain the green, yellow, orange, and red zones at all?
Yeah, I guess I could pipe in on that, Mike, here. There's multiple zones set up. There's what they call the green zone, which is, I'm trying to remember the numbers off the top of my head. Marcia, you can correct me on this too. I think it's about 118,000 or something like that. And above, there's no harvest restrictions for it. It's because of the difference between subsistence users in Canada and the U.S., Jeff. There's no restrictions in that zone. And get into, we have a specific prescription for licensed hunters. And then there's a zone, and again, I don't have the numbers right at my fingertips here. It's like 90,000 to 118, say, and that's yellow. And there's restrictions for licensed hunters, still nothing for subsistence. And then it ratchets down from there until you get to a point where there's no real harvest other than for ceremonial purposes. But those are general guidance zones. It doesn't mean that everything is locked specifically in those ranges. If you've seen a dramatic decline, you could enact the actions of the zone slower, even though your estimate's still above it. So.
Okay. Any other questions or comments?
Mike, these are the different iterations. As far as the upcoming meeting here, this is some of the data you'll be bringing with you, correct?
Yeah, that's right. I don't know, Leonardo. These are the final versions of the specific ones that you presented. But yeah, it'll be along these lines, Jeff. So, changes in harvest rate and sex ratio, and looking at the impact of those different harvest regimes.
Yeah, great.
Yeah, Mike, I've run a lot of the scenarios, and I was just updating the code that produces the figures, because there some small changes that need to happen to that, but I should be able to get you those in the next couple of days.
Okay, perfect. Thank you.
All right. Well, thanks everybody. Thanks Troy for organizing the meeting, and thanks everybody for attending. And if anybody has further questions that come up afterwards, feel free to get in touch either through Troy or directly. I think you have my contact information.
Yeah, great. Thanks much.
Thanks, Leonardo.
All right.
Thanks
Bye,
everyone
everybody.
for calling in.
Thank you very much.